Hello, everyone. I'm Vince Poor, and I'm the third member of this tutorial team. As Yonina said at the beginning, there are really two parts to the connection between machine learning and wireless communications. One is using machine learning to optimize wireless communication networks. And this is the aspect that Yonina and Nir have been talking about so far. The other side of the coin is the use of wireless communication networks as platforms for machine learning. And that's what this third part of the tutorial is about, and what the remaining part of the tutorial is going to be addressing. So I'm going to talk about basically two things in this context. One is so-called federated learning, which I'll explain a bit more in a minute. And the other is decentralized learning, which I'll also talk about later. I'm going to share this part of the presentation with Nir. So the way it's going to go is I'll first talk about some basic things about federated learning. Then Nir is going to talk about uplink compression for federated learning. And then I'll come back at the end and talk about decentralized learning and then wrap up the tutorial. So why don't we get started? So first of all, just take a step back and look at the so-called state-of-the-art, I guess, in machine learning. This is greatly oversimplified, but just to set the stage a bit. So first of all, why has machine learning been such a big thing in recent years? Well, it's not a new technology. Of course, machine learning goes back quite a ways, decades. But lately, in more recent times, we see more and more data being available, both because of the prevalence of personal devices and also because of the internet. And there's been a significant increase in computational power to deal with that data. So this means it's been possible to apply machine learning in a great number of areas. So standard machine learning, and I put standard in quotes because, of course, it's just an oversimplification, but basically standard machine learning is implemented in a centralized manner, that is in the data center or in the cloud. And the learning algorithm has full access to the data. On the other hand, and at the same time, there are also state-of-the-art models, such as deep neural networks, that can be applied in this way. And these are managed and operated by standard software tools like TensorFlow and specialized hardware. On the other hand, there are applications where centralized machine learning might not be the best choice. So examples include autonomous driving or self-driving cars, first responder networks, tactical networks, and others. And what makes these applications different are several features. First of all, the data is at the edge. It's born at the edge of the network, either on iPhones or IoT devices, so it's already there. If you're in a wireless situation, which of course all these are, there's limited capacity to upload data to the cloud. So immediately you see there's a problem. If you have a lot of data to be uploaded, there's going to be an issue. Secondly, in many of these applications, there's requirements for very low latency. So ultra low latency communications, particularly, for example, in autonomous driving. And if you have to upload data all the way back to the cloud, then that's going to add to the latency. Data privacy is another issue because if you keep the data at the end user devices, then its privacy is maintained. I'll say more about that later. And then also just the applications may involve the locality where the end user devices are. And so it's not necessary to think about loading data up from a broad network into the cloud in order to build models. So these kind of considerations motivate moving learning closer to the network edge. So I'm going to talk about here a couple of things, and I'll start with the machine learning, the standard machine learning paradigm I just discussed. You have data which is collected, say, at the edge, uploaded into the cloud. The cloud builds models or a model and downloads that to the end user devices. So the computations are done all in the cloud. The end user devices can be just data collectors, and they don't need to be able to do any machine learning. In federated learning, the end user devices are themselves going to do the learning. So data will be collected at the end user devices. They will learn a common model independently, upload their model to say an edge device, which could be a take the role of the cloud here. The edge device will serve as an aggregator. It will aggregate those models and send the aggregated model back to the edge device or to the end user devices, where it can be updated again, and there can be multiple iterations of this process. And then finally, a decentralized machine learning is a different model where, again, learning is done by end user devices, but then there's no device playing the role of the cloud. That is, all the learning is going to be done on the end user devices. There's no aggregator, but there may be peer-to-peer communications where there can be some consensus achieved about what models should be. So here I'm going to talk about federated learning, and I'm going to talk about decentralized learning. So start with federated learning. What are some challenges? Well, one is just the communication bottleneck. As I said, we're talking about a wireless network. Data has to be uploaded even from the end user devices to an edge device or an access point. So there's going to be a bottleneck there. There are usually many end user devices for each edge or access point device. There's going to be statistical heterogeneity. That is, not every device is going to have the same quality of data. There's going to be system heterogeneity. Not every device is going to have the same capability for computation and so forth. Privacy and security, of course. Once you have a lot of devices in a wireless network, there are going to be possibility of intruders and all kinds of other things. And I'll talk about that a bit later as well. But communications and information theory can help tackle most of these challenges. So if we're going to look here mainly at the communication bottleneck. And in order to handle the communication load, there are going to be a couple things we have to look at. One is user selection. Another is compression and source coding. And then we have to worry about non-orthogonal transmissions, which are going to cause interference. And finally, over-the-air computations, which it means that we may be able to use the actual superposition property of the wireless medium in order to do some of the computations for us. So why don't we move ahead and talk about user selection and interference and how that interfaces or interplays, if you will, with federated learning. Okay, so here's another model, reminder of the model for federated learning. We have end user devices where learning is going to go on. Models are shared with an edge device or access point where it's aggregated and then returned back to the end user devices. Okay. So the basic idea of federated learning is we want to enable those end user devices to do machine learning without centralizing their data. Key features, again, own device data set, so the end users keep raw data locally. On device training, the end user devices are powerful enough that they can train algorithms there on a shared model. Federated computation, they're going to send, the end user devices are going to send their models up to an aggregator, access point, if you will, or edge device, which is going to collect trained weights. So if we think about a neural network, for example, those are going to be aggregated in some way, perhaps averaged. And then that shared model is going to be sent back down to the end user devices where it can be, the process can be iterated. And in this situation, we're going to get privacy by default. And I really should put that in quotes because I'm going to say a bit more about that later. There are some issues there. But if you think about what this means basically that the actual raw data is not going to be transmitted anywhere. It's going to stay on the end user device. So here's the operation, if you will, of federated learning. We're going to iterate the following process until convergence. At the end user devices, we're going to perform local training. We're going to send trained weights to the aggregator. And then at the aggregator, the aggregator is going to average the model. So the aggregator is the access point and redistribute it to the devices. And again, we're going to iterate on that until we get some kind of convergence. Now, what are some issues that come up here? Well, because this is a wireless network, the communications from the end user devices to the edge device or access point needs to go through wireless channels. So the communication medium is shared and resource constrained because it's a wireless medium. So because it's resource constrained, only a limited number of devices can be selected in each update round. And because it's a shared medium, there's going to be interference, so the transmissions may not be reliable for that reason. So two questions that arise here that we're going to address in this part of the tutorial is, how should we schedule devices to update the trained weights? And how does interference affect the training? So here's another way to think about federated learning evolving over time. First of all, there's the access point or the aggregator is going to select a certain number of end user devices for upload. Those devices can train and then send their trained weights to the aggregator. Some of those transmissions are going to be unsuccessful. And then we're going to iterate again. So there's going to be another round of the same thing, and we're just going to keep going until we converge. So the two kinds of things that can happen are, if you're an end user device, you're not selected, and so therefore you can't at that time send your updated weights to the aggregator, or you may be selected and yet you can't transmit because of some of the impairments of the wireless channel. Okay, so here's a system model that we're going to look at for this, so we can try to get some understanding of it. First of all, we have a mobile edge network, so we have access points and end user devices that are capable of computing. The access points we'll just assume are distributed in some kind of Poisson process, and each access point is going to have K end user devices associated with it. And then the spectrum is going to be divided into N subchannels, where N, of course, is less than K. And that spectrum is going to be globally reused from access point to access point. Okay, so one of the first questions we're going to have to ask is how to schedule these users. But first of all, let's just look at the federated learning again. Again, there's own device training. And what's going to happen is each end user device is going to train a statistical model using its own data. The end user devices are going to download a shared model from their access point and perform local computing. Then each access point is going to select N of its K end user devices to update the trained parameters at a given iteration. And then each access point is going to update its model and redistribute it to its end user devices. So this is going to be going on in multiple cells with multiple access points. So now the first question we might ask is, how can we schedule the access points to schedule the end user devices to upload their data on each round? And to look at that question, I'm going to look at three standard scheduling mechanisms, and the idea here is you want to compare their performance in federated learning setting. The first one is random scheduling, where the access point uniformly selects N, remember N is the number of channels, out of its K end user devices at random, so random scheduling. The second scheduling mechanism is round robin, where we just divide the end user devices up into G groups, where G is determined by the number of end user devices and the number of channels, and is just going to sequentially select those groups as the model is updated iteratively. And finally, there's proportional fair scheduling, where the access point is going to select N of the K end user devices with the strongest signal to noise ratios. Okay, so it's another technique. Now, what I'm going to talk about now is an analysis that appears in the paper that's shown here at the bottom of this screen, which appeared just a few months ago in the IEEE Transactions on Communications. Okay, so now we have these scheduling mechanisms. We're going to be transmitting over a wireless network. So a trained update can be successfully received by the access point if and only if two things happen. First of all, the end user device with that particular model has to be selected by the access point, and even if it's selected, the received signal to interference plus noise ratio at the access point has to exceed a decoding threshold, which we'll call theta. So theta is is a parameter of this model, which will come up later. So this gamma sub kt is just the SINR at the received at the access point for the kth end user device at iteration t. And a metric to quantify the effectiveness of training is going to be the number of communication rounds required to reach an epsilon accurate solution. And by that I mean, so here we're going to be solving a very tame machine learning problem, and just to look at the communications aspects. In particular, we're going to be looking at minimization of a strongly convex function. So in this case, you know you're at a minimum when the primal and dual solutions agree. And an epsilon accurate solution is one where the difference between the primal and the dual solutions is less than or equal to epsilon. So when epsilon is small, you're getting to very close to optimum. Okay, so that's what we mean by an epsilon accurate solution, and epsilon is going to be another parameter in this model. Okay, so in this setting, with some assumptions that are found in that paper, I won't go through them all in detail here, we can actually get lower bounds on the number of communication rounds, and they're given here in these formulas. I'll give some approximations in just a minute, but the parameters are, as we've seen, there's theta, which is the threshold for decoding. There's epsilon, which is the quality of the solution. And there are three more parameters, which I didn't mention yet. One is the path loss exponent alpha. Another is the precision level at the end user devices of machine learning. So we're going to abstract the machine learning at the end user devices into a precision level that can be achieved there. And N is just the total number of exemplars distributed over all of the end user devices. So don't worry too much about these formulas. I'm going to give some plots in a minute, but we can also do some approximation for special cases. If we have a high SINR threshold, which means basically a low quality, a lower quality code, so this is a more challenging situation, we can approximate the three lower bounds in this way. For random scheduling, round robin, and proportional fair, basically what we can see with these approximations is that random selection, round robin have approximately the same behavior, whereas proportional fair actually has a lower bound. Okay, so these lower bounds are just lower bounds, but they're going to be proxies for the performance, and we'll see that they also do predict some performance in actual machine learning. On the right is an approximation when the theta, that is the SINR threshold for decoding, is small. This is the case where we have a really good code. We don't need a lot of SINR to decode. In that case, we see that random scheduling and proportional fair have the similar convergence performance, while round robin has better speed up. So for a good channel, round robin is better. For a bad channel, proportional fair is better, as you might expect. And here's a chart just to show that for a particular set of parameters. The left-hand side is for a high decoding threshold, 15 dB. The right hand is for a low decoding threshold, minus 25 dB. And you can see that in the left-hand side, the lower bound for proportional fair is much lower than the lower bound for the other two other two scheduling protocols, and that's just consistent with intuition, because if you have a poor channel, you need to pay more attention to the signal to noise ratios. On the other hand, on the right-hand side, where you have a really good link, then we don't really have to worry too much about that. We can just go round robin and still get good performance. So blue here, the lower one on the right is blue, which is the round robin. On the left, green, which is proportional fair. We can also use these lower bounds to look at the issue of how we should divide up the spectrum. Excuse me. Obviously, if we have larger subchannels, excuse me, we can get better performance. On the other hand, if we have smaller subchannels, we can allow more end user devices to report on each iteration. So there's a trade-off in terms of number of subchannels, and you can see that there's kind of a sweet spot from this chart here on the left. You can see that there's kind of a sweet spot for the number of subchannels for a given type of scheduling algorithm. I'll just show here some actual machine learning results just to underscore the fact that the scheduling protocol matters. So this is looking at a case where we try to, we're training a support vector machine on MNIST data, which is handwritten character recognition data. You see the parameters here, 10,000 sample points on 100 devices. And at each time, we're going to be able to select 20 for aggregating. On the left, we're showing loss, which is, I think, mean squared error. On the right, we're showing accuracy, which is percent correct. And you can see that in this case, round robin, this is a case of a low decoding threshold. I don't think we put it here. But you can see that on the left, round robin does indeed perform much better than random scheduling. Many fewer rounds are needed to get down to low loss, and also up to high percent correct. So the scheduling matters. It matters theoretically, and it also matters in real machine learning application. So a question we might ask is, can we optimize scheduling? And the answer is yes, we can, at least in terms of one metric. And the metric that makes a lot of sense here is the age of information metric, which has been developed for looking at situations where the timeliness of information is an important factor in addition to the quality of the or fidelity of the information that we receive. So here we can think about age of information as being defined in the following way. For a given end user device or device I, during each communication round, if the device is selected, the age of its information drops to 0. Otherwise, the age of information increases by 1. So we have an indicator, a selection indicator. So SI of T is 1 if the ith device is selected in the tth round to be up to upload, and it's 0 otherwise. So if S goes to 1, the age goes to 0. If S is 0, the age just iterates by 1. So we can set up a problem where we can look at this optimization problem. Here we're just going to look at, we're going to forget about the role of interference here. We're just going to look at one access point to focus in on this optimization problem. So again, we have K associated end user devices and N subchannels. And here we're going to allow the end user devices to select more than one subchannel if they want to. Okay, so there are more degrees of freedom here than just which end user devices are going to be selected. So we can set up a design problem where we try to minimize the average age of information. Remember, I of T is the age of the information of end user device I at time T. SI of T is a selector for that end user device at time T. F alpha is just a weighting function for the time, standard one, before the age of information. And then we have several constraints. We have a rate constraint, which plays the role of the, if you will, a role similar to the role of the SINR threshold and the other model that I gave you. There's a total power constraint, and there are channel constraints. There's only so many channels. And so the total number of channels in use is upper bounded by N, basically, and so forth. And so what I'm going to talk about here is basically in another ICASS paper, which you can hear later this week, which is shown here. And so I'm not going to go a lot into the detail because you're going to see, you can see some of the details of this in another paper. So anyway, we have this model. It turns out that this computational problem is fairly low complexity. It can be solved in polynomial time. So at each iteration, we can solve this problem to decide which end user devices should be chosen for upload at that iteration. And when we do that, we see that we can get improved performance over another fairly reasonable type of scheduling algorithm called maximum pack, where at each time we try to pack in the maximum number of reporting end user devices as we can. So here, wireless round robin is the scheme I just described, where you minimize the average age. Maximum pack I just described. On the left, this is a case with high rate threshold. On the left, we see loss. Again, wireless round robin is much better than maximum pack. And on the right, we see percent correct. And again, with the same thing. This is the same problem we looked at before, where we're training a support vector machine on MNIST data. We can also look at low rate threshold, and we see very similar things. Loss is better for wireless round robin, and percent correct is better for wireless round robin as well. Okay, so I'm going to come back in a minute. I'm going to turn this over to Nir now to talk about uplink compression for federated learning, and then I'm going to come back later and talk about decentralized learning. So I'll be back.
Hey, this is Neil again, and I will discuss another relevant challenge of federated learning, which can be naturally tackled using communication tools. Now, this challenge stems from the fact that in wireless communications, and particularly in cellular communications, the upload link is typically notably more limited in terms of throughput compared to a downlink counterpart. Consequently, if in federated learning, the users are required to convey large volume of model updates repeatedly to the server, they must compress it before doing that. Now, this problem has not been overlooked in the federated learning literature, and there are two main approaches to compress the model updates before conveying over the uplink channel. The first family of method can be modeled as sparsifications. Sparsification method imply that instead of sending complete set of model updates, we're just sending a subset. So this can be just selecting a random subset, like by applying some random mask. It can be a subsampling of some random rotation of the model updates, and this allows at some level to convey a portion of all the model updates while carrying out subsampling. This can also be carried out by simply taking the most dominant gradient, which is what's called top K compression. Alternatively, the other family of approaches is based on probabilistic scalar quantization. Probabilistic scalar quantization means that we're taking the model updates and we're adding noise to each one of those updates, where the noise specifically depends on the scheme we're using, and then we're quantizing each one of those model updates. And it can be using ternary quantization. It can be based on uniform quantization, which is what's called QSGD, which is arguably the leading approach for probabilistic scalar quantization in federated learning. And it can also be non-uniform quantization, which is the recently proposed natural quantization for federated learning. Now, all of these approaches aim on representing the model updates using a limited number of bits, where the presence of noise in fact facilitates convergence of federated learning despite the distortion induced by quantization. Now, in order to tackle this problem from communication perspective, we need to understand what is the right thing to do for such a problem based on knowledge in quantization theory, in source coding, and in information theory. To that aim, let us understand what are the requirements for uplink compression in federated learning. Now, first, obviously, what we want to do, we want to minimize the distortion induced by quantization. Now, quantization theory tells us that in order to reduce the distortion, we need to use vector quantizers. Namely, we need to take a set of samples, do some partition of the hyperspace into distinct set, and assign a digital value to each one of those sets. Now, the vector quantization is typically dependent on the distribution of the quantized value. Namely, the partition here depends on the distribution of the model updates. But in federated learning, we also cannot assume prior knowledge on the distribution of the model updates, particularly in statistical heterogenic setups. Now, this motivates the usage of universal quantization schemes. Namely, the partition here has to be fixed, cannot be dependent on the distribution of what we're quantizing. Furthermore, there's another thing we can exploit here, the federated learning setup, And this is the fact that the server and the users repeatedly communicate with one another. Therefore, the server can share a seed with the users, allowing to utilize a source of common randomness. This is actually what's exploited in schemes based on random sparsification. They are based on the fact that even though the sparsification is random, the server knows which indexes were selected. Now, based on these three properties, we can understand what one would do for such a scheme when looking at it from a quantization theory perspective. And this is what we call universal vector quantization for federated learning. It will be presented actually here in ICASSP later on this week. And it's based on the scheme proposed by Zamir and Feder back in the 90s of randomized lattices. To understand how randomized lattices work, this will be the partition of the two-dimensional space into cells. Note that the cells here are fixed and each cell has its centroid, which is a digital representation. And it does not depend on the distribution of what we're quantizing. So let us assume that the model update now we're trying to convey is a vector which lies somewhere here. What randomized lattices do, we first draw around this quantity we're trying to quantize, we draw a cell around it and we randomize a dither signal, which can be treated as noise, somewhere in that cell such that the resulting value is moves from the point of the model update to this point. Then we quantize it, namely we assign it to its closest lattice point, to its centroid, and this is the value which is conveyed over the uplink channel. This is a discrete value, so it can be represented using a finite number of bits. Then, on the server side, we're exploiting the fact that there's a source of common randomness such that the server can know the dither signal to subtract it. And then what we get is a scheme called subtractive vector quantization based on randomized lattices, and it has great statistical properties. For example, for once, it achieves guaranteed low distortion, namely the distortion achievable using this scheme is within a bounded gap from the optimal distortion dictated by ray distortion theory. Furthermore, the distortion induced by quantization here actually is statistically equivalent to additive noise, which does not depend on what we're quantizing, implying that the fact that the model updates are afterwards averaged by federated averaging inherently mitigates the quantization error. And this can actually be proven analytically. For example, if these are the weights at a given time instance, t plus tau, and these are the desired weights which one would have received conventional federated averaging without any quantization, we can actually bound the distance by a term which depends on the squared step size and this sum here, in which recall that those alpha k's are the weighted averaging coefficients of federated averaging, which implies that if we're just doing averaging, namely if these are just 1 over k, then this term here decays as 1 over the number of users. Namely, the more users we have, the less quantization error is induced by this scheme. Furthermore, we also know that in federated learning, the step size typically decays with time. And actually, for statistical heterogenic setups, it is essential for the step size to decay on time. So this implies that this bound here also decays in time when it's in federated learning setups. So the distortion, namely the gap between the weights we are recovered by the server and the desired weight recovered by the server, it can be actually mitigated. It actually grows smaller with the number of users and with the step size as federated learning progresses. Now, the gains are not only translated in terms of quantization distortion, they're also translated in terms of the convergence of the overall algorithm. And it can be shown that for smooth and strongly convex objectives, the distance between the expected objective achieved using this vector quantization scheme with federated averaging and the desired one, the minimal objective, can be actually bounded by a term which grows as 1 over t, which is exactly the same, or at least the same order of convergence as that achieved in unquantized federated learning. Now, these theoretical gains of this approach are also translated into are also observed numerically. And here we consider two scenarios. One is when we're training a single hidden layer network over MNIST data, and here we're training a convolutional neural network over CFAR data. And for both cases, we see that the black curve, which denotes the convergence, the accuracy versus the number of iteration when utilizing vector quantization, when utilizing universal vector quantization compared to utilizing QSGD, for both cases, we see that it both converges faster and converges to a more accurate model. And this also when you don't use vector quantizers, when you use scalar quantizers, but you utilize this approach in which the server also subtracts the dither. So the gain here is twofold. One source of the gain stems from the usage of subtractive dithering, the fact that the server can subtract the noise added prior to quantization. And the second gain, the more dominant one, stems from the usage of vector quantizers. And this is universal, and it's applicable here for those non-synthetic data sets in which are very hard to model using statistical tools. Now, these numerical studies and the corresponding analytical study demonstrate one example of a challenge existing in federated learning, which can be tackled efficiently using tools from communication and information theory.
Hello, this is Vince again. Now I'm going to talk about another way of using a wireless network as a platform for machine learning, namely decentralized learning. And you may remember from what I said earlier that in decentralized learning, we don't have any kind of access point or other aggregator in the machine learning algorithm. The learning is going on only on end user devices. But they may be sharing information with one another in a peer-to-peer fashion to help the learning. And that's what I'm going to talk about now. So just a way to motivate this, we might think about Internet of Things kind of applications, which of course are ubiquitous into types of applications that where they might arise. But some of the salient characteristics of the Internet of Things are, first of all, massive connectivity. We're interested in high energy efficiency, which means we may not want to transmit very far over network in terms of network distance, low complexity terminals, light infrastructure, and so forth. So this is, for example, we may not have an access point per se that we can transmit all data through, and so forth. So some of these characteristics of IoT are ones that might motivate the kind of decentralized learning that I'm going to talk about here now. So to talk about decentralized machine learning, first of all, I want to back up and look at a general model for distributed learning. This model involves looking at learning in the terms of a bipartite graph. And one part of the graph consists of training examples or exemplars. So a training example is basically if we think about we're trying to train a model, we have input to the model X and output of the model Y, and we have examples of those inputs and outputs, and we'd like to do something to train the model that maps X into Y. So that's basically the machine learning problem that we're trying to address. So we have a training database of N samples, and this is one part of the graph. And then we also have learning agents. So they could be smart sensors, for example, or they could be access points in a general model, or anything in the cloud. And we have M of those. So this is a model that, and then there's connectivity between the two layers of the bipartite graph. So a learning agent is connected to a training datum if that learning agent has access to that training datum. So this describes the learning agents and the data and which agents have access to which data. So there's some specialized cases of this. Centralized learning is one special case. So you have one learning agent and it's connected to all the data. So that's centralized learning. Federated learning is another example where you have a small number of learning agents connected to a large training database. So the training database would correspond, say, to the end user devices. And then the learning agents are or access points are connected to their own devices in their own cell. Or you can think about decentralized learning, where there are the same number of learning agents as there are training data. And in fact, the learning agents are the data collectors themselves. And that's what we're going to talk about here. So in that case, M equals N. So now one natural way to do learning when you have this bipartite graph model is to think about local learning. So you have learning agents connected to data. So each learning agent has some data points and it can simply learn a model from those data points. So for example, if we think about kernel regression, kernel learning, We can think about trying to learn a model, a function f that maps x to y. And we can do that individually from learning agent to learning agent using whatever data is available to each learning agent. And that's called local learning, basically. So that's a very simple and obvious way to try to take advantage of this model. On the other hand, it turns out that local learning is locally coherent. And what that means is the following. If two learning agents share a training datum, but not exactly the same group of training data, they're going to learn different values of the mapping f that maps x's to y's. So when those individual f's are applied to, say, x1 to a common data point. So here I'm thinking of f1 and fm sharing the data point x1, y1. F1 hat, the learned function for F1, for agent 1, may not agree with FM hat and when applied to X1. So that's called local incoherence. So even though they're training with the same single data point, their other data points are different, and they're going to get different values for the target on that shared data point. So this is local incoherence, and it can be shown that local incoherence is not optimal. That is, you don't get the overall best fit of learning when you do that. So the nice thing about local learning is that it requires only local communication, but it leads to local coherence, which is undesirable. So we might ask the question is whether agents can collaborate to gain coherence while retaining the efficiency of locality. And the answer is yes. And the answer comes through this paper, which is actually more than a decade old now, which appeared in the Transactions on Information Theory in 2009. And let me just explain that briefly. So we can look at a collaborative algorithm where we do maintain locality, but we have a way of getting around incoherence. So let me just describe this algorithm briefly. So we have, in this case, we have 4 learning agents. The first one is going to train on its data. And then when it's done training, rather than just moving on to the next agent, the estimated targets are from learner 1 are going to be written into the training database, overriding the actual targets. So F1T of X1, which is the estimated target for training data 1, is going to be written at time iteration T from learner 1, is going to be written over Y1. Then we're going to move to training agent 2, which is going to do the same thing with its data, learning its version of F, and then writing over the targets in its data. And we're going to iterate around and around until we get to convergence, okay? And it turns out that by doing this, we get global convergence to coherent relaxation of the globally optimal solution, that is the centralized solution to this machine learning problem. And you can prove that by using alternating projection. So it's not even that hard to prove, actually. So here we have we only need local communication, but we can get basically the best performance that we can get, and we can get a coherent solution. But we can just look at an example of this. Here's a case where we have 50 sensors lined up along a line between -1 and 1, just randomly deployed. Each sensor is going to observe a function of its location, xi, plus noise. We'll just assume the noise is IID normal 0, 1. In this case, the function f is going to be linear, so this is a very simple problem. And then we're going to let two sensors be neighbors, or two learners, if you will, be neighbors if they're physically within R of one another. So R is kind of the radius of a neighborhood in this case. And the sensors are going to do kernel learning, and they're going to apply a linear kernel. So this is a fairly simple machine learning problem, but it does illustrate what's going to happen here. So if you look on the right, we show test error versus R, so versus the size of the communication neighborhoods for each sensor. And down at the bottom, there's a solid of this curve. There's a solid line, which almost is at 0, which is the fitting performance of centralized learning. And here, since we have a linear kernel, a linear regression function, of course, it's going to be a very good fit. The dotted line, the one at the top, is local learning. And you can see here that the radius R has to be quite large in order to get close to that centralized learning. In fact, you almost have to have a large enough radius that all the data is in the neighborhood of each other. On the other hand, if we do SN train, which is the dash dotted line, that's the algorithm I just described, you can see that with a fairly small neighborhood, R equal 0.2, we're already down to the performance of centralized learning. Okay, so you can see that this collaborative learning algorithm is actually quite powerful in maintaining the advantages of locality while getting pretty good performance out of the learning algorithm relative to purely local learning. I want to talk about one other topic in this area, and then I'm going to wrap up the tutorial. First of all, this has to do with a different learning problem, which is reinforcement learning. Now, reinforcement learning is not really a problem of minimizing a function through learning. It's really a function of finding decision and control strategies without a model in Markov decision processes. And a particular type of reinforcement learning is Q learning, which is trying to update a Q function, a utility function, iteratively, seeking to converge to an optimum to find a decision strategy or control strategy that gives us the optimum utility. If we have a centralized data for reinforcement learning, the update is typically performed by gradient updates. Okay. On the other hand, in a distributed setting where we have decentralized learners, we can't really do a centralized gradient update, so we have to do something different. But it turns out that in an algorithm that's described in the paper that's shown here at the bottom, which appeared in the Transactions on Signal Processing in 2013, in a fully distributed setting, we can in fact find an algorithm that does achieve global Q values under certain conditions on connectivity of the bipartite graph that I showed you. And in particular, in a fully distributed setting, at each agent, the Q function is updated not only by using a local gradient update in a classical way, but also trying to achieve a consensus among neighbors. So you have two parts of an update, gradient update plus a consensus among neighbors update. And if we do both of those updates and we have the right connectivity, and we choose the tuning parameters of the iterative algorithm in the usual way, then we can get convergence to global values. And so we don't really need centralized reinforcement learning under these circumstances. So just to show an example, this is a very simple example of reinforcement learning. We have 40 learning agents. The states are binary, the actions are binary. Connectivity, it depends on the two nearest neighbors are your network or your neighborhood. And on the left here, we look at the Q factors, of which there are 4 here because we have binary states and binary actions for a typical agent, for centralized and distributed iterations. And you can see over time, these both converge to the same thing. So we're getting centralized performance out of this decentralized algorithm. On the right, we've chosen 10 agents at random, and we're just looking at how they achieve consensus. Again, there are 4 Q factors, and we're seeing that they're all converging together for these 10 agents. So just as in the case of other types of learning, when we have a decentralized algorithm, if we do it correctly, we can get centralized performance. All right, so let me wrap up this final part of the tutorial, and then I'll wrap up the tutorial. First of all, we've been talking here about using wireless networks for platforms, as platforms for machine learning. We talked about federated learning, where edge devices like access points interact with end user devices to learn common models. Then we talked just now about decentralized learning, where the end user devices interact with one another to collaboratively learn models or actions in the case of reinforcement learning. Some issues for research here. First of all, we haven't really talked much about the fact that resources on end user devices are limited. That is, there's limited computational power, limited energy storage, and so forth ability particularly on sensors, but even on smartphones. So there are fundamental trade-offs between things, like if you're using a neural network, how many layers, how many neurons per layer, how much energy are you willing to devote to learning, what accuracy do you need, and so forth. These are all things that deserve exploration. Communications efficiency, we already talked about that. The fact that we can do uplink compression is one way of achieving efficiency. Another way of achieving efficiency is to do distributed source coding, recognizing that data may be correlated from end user device to end user device. Also, we have limited data at the edge. So local data is sparse, training sets are small. We don't really have big data here. This is not a big data type problem that we're talking about when we're learning on the end user devices. So it may be useful to incorporate domain or physical knowledge into the learner. An example of a technique we might use there is deep unfolding, where we can, which is a general mechanism for incorporating knowledge into iterative algorithms. And finally, I'll just mention security. Again, this is a wireless networks we're talking about. There's possible malicious end user devices. There can be adversarial training examples injected into the system. So there are issues here that need to be considered, and people are looking at these kind of problems. I didn't write it here, but privacy is another issue. You know, we get privacy by default, at least we think we do in these algorithms, but it is true that you can make inferences about the end data from the output of machine learning algorithms. So there's still some things to worry about in terms of privacy as well. And then finally, let's wrap up the tutorial. So what have we talked about? We've talked about two very exciting growing areas of technology, machine learning and wireless communications. Neither of these is really a new technology. They're decades old, but they've come to be they've evolved very rapidly over these decades, and now they're quite sophisticated. There's also a lot of interactions between the two, as we've seen in this tutorial. We can use knowledge from one to contribute to the other, and that's what this tutorial has been about. There's just a multitude of new research directions, and we've barely touched on them here in this tutorial. So of course, we're open to ideas, questions, and insights from you. We hope you enjoyed the tutorial, and we thank you for your attention. Before I finish, I just want to mention that there's some other ICASS papers that are in this general area. I'm going to leave this up for just a minute so you can see what they are. I mentioned the second one here. That's that one that uses age of information. Some of the others here have been mentioned throughout the tutorial, and these are going to be presented later this week in ICASS. So I hope you'll be able to enjoy some of those. So thank you again, and we look forward to hearing your questions.